Hi there. My name is Neil McIsaac, and I'm a Microsoft Technical Trainer. In this video, we'll be focusing on running experiments using automated machine learning. We'll start this session by introducing what automated machine learning is, followed by how to find the best model using it. We'll also spend some time on introducing ML flow and how it can help with tracking and managing your experiments. So let's get started with what automated machine learning is all about. One of the biggest challenges with doing machine learning is deciding on which algorithm, as well as all of the best values for our hyperparameters that will give us the best model. Typically, data scientists are going to spend a lot of time choosing and configuring algorithms, then train a specific model using those settings, and then spend time evaluating the performance of the model. And then, after all of that, repeat the process with maybe a different algorithm with different settings to see if they can improve on the model performance. Essentially, there's a lot of trial and error in the overall process. Now, to give all the data scientists out there credit, their knowledge and skills greatly reduces this process, but there's still a lot of trial and error overall. So, wouldn't it be nice if we could simply throw compute at the problem? In other words, what if we ran multiple experiments with different configurations, such as different algorithms and different settings, all at the same time, and we let the service evaluate the models that are built from each experiment run to determine the best model for our situation? That's exactly what automated machine learning does. In essence, we can kind of brute force the problem by running many experiments with different configurations all at the same time. And at the end of it, we can see which model performed the best and how it compared with the other models that were built. Then you might be thinking, well, what's the role of the data scientist in this case if the service can just determine the best model for us? Well, that's a great question. I would absolutely say that the data scientist is still very much needed with this process because there's still a lot of work to do. And their knowledge is needed to really get the most out of AutoML. And there's still a lot of tasks that AutoML can't do. So the benefit here, and this is true even if you're a data scientist, is that AutoML can reduce the time it takes for you to evaluate multiple experiments at the same time. That's assuming that the models that you're evaluating are supported in the AutoML service, which is likely since it supports a lot of the common algorithms that we typically use. AutoML supports algorithms in these 5 categories. Classification, which is used to predict a categorical value, for example, classifying support tickets into different categories like technical issues or billing inquiries or general questions. Regression, which is used to predict a numerical value from other values in the data set. For example, maybe to predict housing prices in a particular market. Time series forecasting, which is intended to predict future numerical values based on a time series of data. So the easy example on this one is stock market predictions. Computer vision, which is used to classify images and detect objects within images. And natural language processing, or NLP for short, which is used to do text classifications or named entity recognition, which is essentially to do processing of text. Within each of these categories, AutoML supports a number of specific algorithms that can be configured for experimentation. So how do we use it to find the best model? Let's look at using it to find the best classification model. Before we run any experiment, we need to prepare the data. The same is true if we want to run an AutoML experiment. So to get started, we need to create a data asset in our workspace, but more specifically, it needs to be an ML table. If you recall, ML tables store the schema for your data in an ML table file and can provide the data in a tabular format by using that schema definition. On the slide here, you can see an example of specifying the ML table in a Python script by setting the type parameter to ML table and specifying the path to the data asset that we're using. Part of preparing our data for processing involves configuring scaling and normalization to help provide the best data to train our models with. Scaling and normalization help to balance the weight of different features, so we don't have any large-scale features dominating the training. AutoML will automatically apply a number of scaling normalization techniques to the data for you. There are also a number of featureization settings that you can configure for AutoML to automatically apply to the data, such as imputation for missing values, categorical encoding, which is used to convert text categories into numbers, automatically dropping high cardinality features such as row IDs, and feature engineering such as separating datetime features into the individual date part features. One of the bits of feedback that I often get about these settings is that many data scientists feel that they don't have as much control over the data since we're really letting the AutoML service determine most of it, and we have very limited control over those settings. Basically, our control is mainly limited to enabling or disabling those transformations on specific columns. However, remember that before we do any experimentation, we need to prepare our data first. So if you want more control over these transformations, just do them before we pass the data to AutoML for processing. Essentially, this is the exact same process that we would do if we were doing our experiment much more manually. All right. With that, let's move over to the portal and see how to create an AutoML experiment. All right, so let's start off with going over to the Automated ML page here. And what we're going to do is we're going to set one of these jobs up completely within the GUI. So we're going to start off with a new Automated ML job. And this is definitely one of the easiest ways to approach this, even though usually we'd do this with a script. So let's give this a name. And I'm going to keep this simple, so we'll just keep the new experiment name as default. We'll put a description in here. The thing about this is just we want to show what this does, right? So we hit next. We need to go and pick the data as well as the task type. So let's start with that. So this is going to use we have a choice of a bunch of them, but we're going to use the classification option here because we want to classify whether or not somebody has diabetes. We're going to use the diabetes training with this. So this is similar to the data that we've seen in previous data. So we have all kinds of data in here, the patient ID, pregnancies, things like BMI, all that stuff. All right, so we have data. We want to classify it. We're going to go next. And the next thing we're going to set up is we're going to start diving into some of the details of how we want this to behave. So what is the target column that we want to predict? In this case, we want to find out whether or not, predict whether or not somebody might have diabetes, whether they're diabetic or not. So that looks pretty good. And the next part, and this is part of the interface that it's almost it feels a little bit hidden. So I want to show where these are. So under the additional configuration settings, we can specify what metric we want to use as the primary metric on how we're going to rank all these models. So we can use like AUC weighted, accuracy, and it really depends on which category we're choosing previously. So in this case, because it was classification, we can do this. Next, we want the explain the best model. In this case, we also have the option to do ensemble learning, which is going to take multiple models and use them together to generate a model. So that's an option that we can play with as well. And we can this next part to a lot of people the first time seems a little confusing. So this is use all supported models, and then right below this we have a list of blocked models right here. And so this is saying, hey, use them all except for these models. So let's select a couple. Let's take maybe it is a pretty good list here. Let's take random forest, extreme random trees. I'll take decision tree. We'll just have a thing against trees, right? Maybe so something like that. And when we do this, it's going to use all the other algorithms except that. Now, what's interesting is we can reverse this. So we say don't use all of them, and then that changes to allowed models. And now this is going to be what we want to pick off the list. Say we want to use, logistic regression. Let's take KNN and SVM and decision tree. So only these algorithms are going to get used in this case. So it's really up to us which way we're going to do this. I'm going to switch it back, and let's just open it up to everything in here. Okay, so a lot of the configurations about how this is going to behave. So it's not too bad here for what models we're going to use it. And as a data scientist, you can control that, of course. So let's save that. The next page we're going to look at is the featureization settings. So this is going to be how the automated ML feature is going to go through and actually play with the data. So first off, like the feature type. So for patient ID, for example, that is, has a really high cardinality. Probably shouldn't be here. We'll, as we run it, it can determine that. But the feature type is going to be, well, what type of data is it? Is it numeric? Is it date, time? What's going on here with it. So you just want to make sure that the service can actually recognize any of the columns for what it is. Now, imputation, if we have null values, how should we replace those? Is it do we use a median filled with a constant? And for these, I'm just going to leave everything set to auto. It actually does a pretty good job to determine a lot of these. So both of these are set to auto here. And we can do that for any of the columns that we're providing as our feature data coming in here. So not too bad. And we can see a data example for any of it too. So let's save that. And let's talk about limits. So on the task settings, we can place limits on everything. So the total number of trials, concurrent trials, the maximum nodes, things like the score threshold, any experiment iteration timeouts in there. And so that's going to really help us reduce the amount of compute that we're using. We don't really have to try and kill this with trying to test every single model. We also support this, early termination in here as well. So we find that trials just are not producing better results. We can say, stop, for them. And so this is all, again, it's automatic. We're really just doing some high-level looks at what we're picking, how much compute we want to spend on everything, and totally up to us. Now, of course, we want to validate our data, so we can do the validation. In this case, again, it's automatic, so it actually can work through that. But we can be more specific if we want to, and we can also specify what we're going to use for test data, right? So our test data, we can just do the typical train test split, where we take our the data that we're providing and split it up and use it for testing, and then how much of a percentage we're going to use, right, from our training data as test data. So in this case, just leaving it at 10%. We can do that. All right, let's move on. Next, compute. So once we configure all this, this is going to spawn a job with a lot of other jobs. We have a few different compute options here. The compute cluster is the one that is very typical because we're probably doing a lot of data, but the new one is serverless, right? This is really a really great option. And again, this is really like compute on demand. We can still configure this, right? CPU, dedicated, low priority, all of those settings. And this goes back to talking about compute. All these settings are really there to say, this is how we want this to behave. So again, low priority is when we have compute on sale. Just remember that it is something that if we are low in the extra capacity in our data centers, then we may actually preempt the low priority. So it's a great discount, but question mark whether you can use it. So if you need this to absolutely run, leave it dedicated. With AutoML, it might be an opportunity to use low priority because we're just trying to figure out a lot of the beginning of our processing, of our model evaluations. All right, so once this is done, this is going to show up as a job, so I'm just making that go. Let's get rid of that. And do remember that this is going to be like a master job, a parent job that's going to go and spawn a bunch of child jobs in here. So we'll look at that later on. So that's submitted. This is going to spin off a whole bunch of jobs, figure out all those models, rank them, figure out what the best one is, and continue on. So, child jobs are listed here. This is just spinning up. So, we could, might be a little quick to go and jump in that right now, but eventually we could go see that, especially when it's done. Okay, let's do another one. In this case, we're going to show the Python SDK version of it. So I just jumped over to a notebook here really quick. And on this one, we're going to really do this pretty much the same process. We're just doing it in code. So this is everything to do with our data, our input data. And notice it's an ML table type. That is required for these. And so we have our training data. Moving down a little bit, we're going to create, right in here, it's an AutoML classification job. So right here, we see it's a classification job. And then the settings for it. So what do we want to name it? What is the primary metric that we're trying to calculate for it? How we want to validate it. Do we want to enable that model explainability? That's going to be for that the winning model. We can set any of the limits on there on the job. So it's just setting a lot of properties, similar to what we saw in the interface. We can do that all right here. So number of trials, all of that stuff is in here. And then of course, setting the training. We can set the training up to block certain algorithms or to enable certain algorithms compatibility. So it just comes back to what I was showing you in the interface to say this is what I want, how I want it to behave, and what's on the list to use and what's not on the list to use. Okay, that's all optional. So once we have all this, we can go. Let's queue this up to run. All right, so. Yeah, let's go run this. All right, so let's get that cell running. I was thinking I was forgetting something, and now we have a classification job that's being set. So this goes really fast because we haven't submitted it yet. So let's get that submitted as a job. Right, so there's our classification job. We're going to create or update the list of jobs using it, and then we're going to see the status URL on it. All right, that's all this code really does. So let's go run this. Now, do keep in mind that AutoML is going to be spawning all these jobs. So this is not a quick process, right? This is still the parent job that's listed here. It's going to run off, spawn that parent job. Things like featureization is going to be a child job. We're going to have a bunch more child jobs to do all the model training for everything. So right now, we really just need to sit back and wait. So while that's going, let's jump back over to some content and talk a little more about what's going on here with AutoML. So while our AutoML experiment is running, which can take a while, let's review the code that we used in the demo when we were using the Python SDK. In the code on this slide, we can create an AutoML job by configuring the type of model that we want to train models for. In this example, specifically, we can see the AutoML.classification function being configured to specify the compute, the name of the experiment of the training data, the target column name, which we're trying to predict, which metric we want to use to rank the models, which in this case will be accuracy, the number of cross-validations that we want to use to validate the models, and lastly, whether we want to enable the model explainability for the best model run. We can also set the limits for an AutoML experiment. This can help us to avoid wasting money on compute calculating models that likely won't produce better results. We're simply trying to help control our costs. In order to do this, we simply set some limits, which you can see an example of in the slide here using the Python SDK. In this example, we're using the setLimits function to set the parameters of the classification job that we specified on the previous slide, and we're setting the timeout minutes that the job will be limited to, which in this case is being set to 60 minutes. We're also setting the trial timeout minutes to be 20, which restricts the maximum number of minutes that a single trial will take. And we're limiting the maximum number of trials to be limited to 5. We're also setting the enable early termination property to be true, which will allow the AutoML process to end the experiment early if the score isn't improving in the short term. All of these settings can help us to restrict the amount of time being spent calculating the different models, which in turn helps us to limit the amount of compute that we're using. Once we configure all the settings for the AutoML job, including any of the limits we might place on the job, we can then submit the job using the Python SDK by calling the create or update method of the jobs class in the ML client. One thing to note here is that when we submit an AutoML job, that job is going to produce a number of child jobs. So each model that is going to be trained will be done within its own child job. So you can think of the AutoML job as being the master job that will spawn all of the child jobs. Also, the featureization process will also be done within its own child job. When the AutoML job completes, we can examine the job in the studio, where we can see the winning algorithm with the other top models listed in the order of the metric that was used to rank the models. In this case, we can see that the winning algorithm was voting ensemble that achieved an accuracy rate of 0.953. And since it was the winning algorithm, and because we had the enable model explainability setting set to true, which happens to be the default, we can view the explanation of the model if we want to. So let's go back to our workspace and see the results of our AutoML job. Hopefully it's all finished. Let's see. All right, so now that everything's finished, actually not all of it's finished, so the two jobs that we spawned, we have one that's still running there. So you can see that the AutoML job that I did in the interface is still running, and that's because I didn't put any limits on it, my bad. It's just to say that, hey, it's gonna do a lot more. The other one that we did in code is completed because we actually limited the number of trials to, I think it was 5 when we created, so it's actually pretty small. So here we can see the parent job. I love the names, by the way. It's like, icy garlic. It's, under, they're just random names for it. And then below this, we see a bunch of the child jobs, including the one that was the best, right? Because that also had a job to explain it. And so you can examine any of these jobs when you go through it. They're all listed here, and we can drill into all of them as we go. So, this is pretty neat. It is important to realize that, when we run this, it's possible to get a lot of these generating, and that's the one I did. The one I just expanded there, I was clicking through things, was the one I did in the interface. I didn't put any limits on it, so there was a lot more of those child jobs. All right, let's look at the icy garlic job. That was the script one. So it's completed. Right, it's all here, and we can look at the models and the child jobs, for how this ran. So let's take a peek at that. On this list, we see the algorithm that really won. Right, it's the voting ensemble, and because it was the winner, and we had the explainability on there, we see that link, and also the accuracy that it won with. Right, so 0.953. For it. So let's jump over to the explanation to see, what this model actually kind of figured out. So when we look at the explanation for the model, there's a lot in here. I'm not going to explain a lot of it. It is the child job that we're actually looking at with the explanations, but we can see things like the feature importance, all of these things to explain this model. So you can drill into it, why this one's pretty good. So a lot of information. We're not going to go through every little bit of this, but it's pretty neat. The witty carpet job. Okay, let's go back to the parent. The icy garlic job. I love the names, and we look at the models and child jobs in here, right? We can actually see which algorithms are used for all of these, and if we had a lot more, we could go through all the pages and see what's going on with it, and so that isn't too bad. And we can see the accuracy and everything for all of them. Okay, we can also look at data guardrails, and so if you recall, looking at any of the automatic featureization that was enabled. This is where when it's automatic and it looks at things. So. To make sure that any of the normalization and scaling options are really applied to the data as much as AutoML will really support, right? So from here, we'll see that it evaluated whether or not we had any missing feature values that we needed to impute. In this one, there were nothing that was missing. It's all passed. All right, so our training data was pretty good for that. the class balancing detection, just above it, down the bottom, high cardinality feature detection. And again, all of these passed, no problem. Keep in mind, the one that we did in the script, it actually used slightly better data than the one that I demonstrated with doing it in the interface, right? I didn't clean up a lot of the stuff in the interface. Like the patient ID was actually in the interface version of the AutoML job that I submitted. Anyway, so this actually had pretty good clean data, which is pretty ideal for what we want, right? So that, ideally, we've already cleaned this up before it ever gets here, and we don't want AutoML kind of guessing. It does a pretty good job of it, but as a data scientist, I really want to have much better control over it. So, all right, let's see, what else? Models and child jobs, we talked about in here, so lots of things that we can drill into. The accuracy, you can, as a reminder, you can play with what metric you're using to rank these, right? That's totally up to you. And I think we're pretty good. So one of the challenges of training several models is being able to group related models together so we can compare their training results. That way we can separate models that are focused on solving one business problem away from a different set of models that are being developed for a different business problem. The way that we group models together is by using experiments. And a simple way of thinking about experiments is you can think of it as a label that's applied to a model so that when we view an experiment, we can see all of the models that have been labeled with the same value, aka the experiment. So to make this a little more complicated, it's possible to do model training outside of the Azure Machine Learning workspace. So imagine for a second that a data scientist trained a model on their laptop. How would we know that it even exists? And to take that a step further, if we did know it existed, how would it align with the other models that we've trained within the Azure Machine Learning service, for example? The way that we would manage that is by using the MLflow library. The MLflow library is an open source library that is designed for tracking and managing machine learning experiments, and it allows us to log our model training to the Azure Machine Learning workspace by using the MLflow tracking component. By doing that, not only do we get visibility about the model being trained, even if it's been trained outside of the machine learning workspace, but we can also track the details of the experiment, such as the parameters, metrics, and artifacts of the experiment. Since this video is focused on using AutoML, it's worth noting that many of the algorithms that AutoML uses supports autologging, which means that all of the details of that model run, such as the parameters and the metrics that are used, will be automatically logged for you. If you want to use MLflow, you will need to ensure that the libraries are installed in the environment that you're using for training. If we're talking about compute inside of the Azure Machine Learning workspace, such as compute instances, clusters, or the serverless options, MLflow is already installed. If you're doing model training on compute that is outside of that, such as on your own device, like a laptop, then you'll need to install the MLflow package, as well as the Azure ML-MLflow package into your environment. After the MLflow packages are installed, the next thing that we need to do is set the tracking URI to your Azure Machine Learning service. You can find this tracking URI on the overview page of your service in the Azure portal interface. The next thing that we need to do is to set the experiment name so that the information that MLflow provides for machine learning workspace will be properly categorized with an experiment. That way, if we have other models that are being trained from other environments, or if we have several runs of the same experiment, we can then compare the results together under one experiment. In order to do this in the Python SDK, as you can see on the slide here, we simply use the setExperiment function and set the experiment name to the name of the experiment that we want to use. We'll be discussing using MLflow more in a later video. And that brings us to the end of this video about using automated machine learning to create experiments and to test many algorithms and settings at the same time. We also managed to sneak in a little bit of an introduction to MLflow and how it can be used to help with the tracking for our experiments, even if they're being executed outside of the Azure Machine Learning service. I hope that you've enjoyed this video, and I hope that we see you again as you continue on through this training series on the Azure Machine Learning Service. Thanks for watching.